Hi, folks. Welcome to the network segmentation mechanisms by Mike and Navia from IBM. You're in the network management stream, this GS UK 2025 virtual conference, and just about to hand over to Mike and Navia.
All right, thank you. So what we're going to talk about today is something called network segmentation. Hopefully, most of you are familiar with it. It's basically a mechanism to allow us to break the computer network into smaller sections or subnets.
Hi, I'm Navya Ramanjulu. I'm the zOS Communication Server Security Architect. So I'll be joining Mike as well on this.
All right. Yeah, before we get started, as with all presentations, this definitely was a team effort. We didn't have all the knowledge here, so we did reach out to other people in our group, and we just wanted to kind of acknowledge them here. And this specific presentation is focused solely on the TCP/IP side of things. With Communication Server, we have two different protocol stacks. We have the TCP/IP protocol stack and the SNA or VTAM stack. We're not going to have any topic discussion here on the SNA side, but we wanted to at least point you to a white paper where we do talk about how you can secure your SNA environment. This is solely on the TCP/IP side. So the agenda, it's kind of a busy agenda. I'll take us through the first couple of things, and then I'll hand it off to Navia to finish it up. But we'll talk about, what's the need for segmenting your network, and there's different types of network segmentation. We'll talk about the physical segmentation as well as the virtual segmentation, and then Navia will take us into the actual logical segmentation, which is a lot more software based. So why would you segment your network? Well, as I mentioned before, the segmentation is really a practice of, taking your computer network and dividing it into smaller, more isolated sections. What that does is it helps kind of reduce the attack surface. So when you're isolating segments, then any attacker who might compromise a specific segment, they're really limited in their ability to kind of go and access other parts of the network. There's also, so that kind of helps limit the lateral movement. Once an attacker gets in, they can't really spread across to other areas within that network. So just from these examples here, for example, if something happens in bank 1 on the right, if you have the correct network segmentation in play, you can basically prevent that attack from bleeding into bank 2 or bank 3's network as well. It also kind of improves the security posture. So what that means, it allows for more granular security policies and controls. Specifically, you can, apply different controls to the different segments depending on what the security needs are for each of those segments. And so taking the picture on the left here, administration might have a lot less, lot different security requirements than, for example, the credit card payment processing system. And finally, this is really about, enhancing compliance. So basically, there are a lot of regulatory standards. There's DORA, PCI, et cetera, GDPR. This kind of helps play into that. So how do you do network segmentation? Well, there's two different kind of types. There's like macro versus micro segmentation. And what is really the difference between the two? Well, from a granularity standpoint, macro segmentation is a lot less granular. You basically split your network into a lot larger segments versus a micro segmentation where you really go down to almost like an application by application or workload level. From a security focus, the macro segmentation is just kind of a general isolation, whereas for micro segmentation, you basically have a lot more precise control, and you can tailor your security environment within each segment. Obviously, with macro segmentation, the implementation is a lot easier. It's going to be a lot more complex with the micro segmentation because you potentially are developing these policies and rules on an application or workload basis. Similarly, the cost for macro is going to be a lot cheaper, but you do get a lot more enhanced security and adaptive policies with the micro segmentation. Now, in terms of here, we talk north, south, and east-west network access. Hopefully, most of you are familiar with what that means, but essentially what it means, if you're not, for macro segmentation, what north-south network access really means is protecting the network that enters or exits your organization from an external endpoint. Whereas east to west access is really once you're in your network, going laterally between the different nodes. So that hopefully will help clear that up as well. Okay. So we're just going to talk about the OSI layer. Hopefully most of you are familiar with it. We won't bore you with too much of the detail. But the key thing here is as we talk about all these different types of network segmentation, segmentation can apply to all these different types of layers. So for example, in the first layer we're going to talk about is the actual physical hardware, how you can isolate network just using different network, adapters, for example. Layer 2 is really how do you pass these frames across to different devices. And when we start talking about, virtual LANs or VLANs and VMAC, that all kind of applies into this layer as well. The networking layer is the IP layer. And essentially what that is how do you route packets between the nodes in the network so that you can actually then kind of do isolation as well, basically dictating where packets can get routed between the different nodes. Transport layer, this is your TCP, UDP, raw kind of layer. This is where how you basically use the IP layer to provide either reliable messaging such as TCP or connection-oriented streaming versus UDP, which is more datagram and an unreliable protocol. But it's essentially the way that applications decide how they want to transmit their packets. The API layer, that is actually just the programming layer. That's the interface where applications actually will get into the networking stack and either send or receive packets over the network. And then the final layer, obviously, is the application layer. These are your KICs, your DB2s, et cetera, where you actually require network access. Okay. Now, the key thing as we go through these is network segmentation. You don't do this in a vacuum. So you don't just go into zOS and specifically do your things without really understanding what the other parts of your enterprise network is doing. So the key here is you have to coordinate what you want to do with your segmentation solutions to be consistent with everything else that's going on in your enterprise. All right, so going into the next topic, physical segmentation. This is actually, a macro segmentation. This is kind of an easy and a cheaper way of doing things. There's not a whole lot of configuration here. So essentially what you want to do is if you want to separate, have your different network segments, you can basically just create different LANs for different types of work or different systems, for example. And the way you do that is you either, you use different network interface cards. On zOS, we have both OSA and Rocky Express for within a specific System Z CPC. We have what's called hypersockets and internal shared memory. These are essentially technologies where there's no actual network or physical network, but it's memory-to-memory communication between the LPARs in a CPC. We also have, and we'll get into it in a little bit, something called hypersockets converged interface. Well, essentially, it basically converges both the OSA and hypersocket interfaces to be the appearance from a TCP/IP networking standpoint as a single interface. And we'll get into that a little bit more detail. We also have what's called cross-coupling facility or XCF interfaces. These are the CF interfaces that are used to talk with the coupling facility. When TCP/IP joins a sysplex, and we'll talk about that a little bit when we start talking about dynamic VIPAs as another type of segmentation. But when you join a TCP/IP, when you join a sysplex, what TCP/IP does is it communicates with all of the other TCP stacks in that sysplex. And what it does is it uses these XCF links in order to communicate with systems that are on a different CPC. These are not recommended to be used as your real networking interfaces. That's where your OSAs and your hypersockets come into play. But these are used by default to basically do communication between the TCP/IP stacks. So what's nice about this is it basically does give you complete separation because you have entirely different physical hardware for each of your network segments. Now, this does increase the cost because you're going to need new, additional network interfaces. You're going to need different switches. You can't plug these in the same switch because you are going to, they're going to be on different physical networks. So it does require a little bit more cost upfront as well as careful planning of it. But in terms of isolation, this is about as good as you can get for complete isolation because they're completely different physical hardware. Okay. How HyperSockets works, to provide isolation, as I mentioned, within a given CPC, there is an internal network called HyperSockets. There is actually more than one HyperSockets that you can configure. They are based on the channel ID or the chipped definition in your HCD definitions. But essentially what you can do here is you can, in this example here, we're isolating the zOS LPARs on that CPC with the Linux on Z LPARs or the Linux ZVM LPAR that's running on the CPC. So by configuring different HyperSocket channels, essentially now you have complete isolation, even though they're in the same machine and they're using memory, they're using different memory because they are different representations of the HyperSocket. So zOS LPARs 1 and 2 can communicate, but they cannot communicate over HyperSockets with the Linux and the ZVM because they are completely isolated based on the definitions. We also have physical segmentation, which I called earlier, this HyperSockets converged interface. Essentially what this is a little bit of a complicated topic, but we'll just kind of touch on it a little bit. But essentially here, what we do is previously, but prior to this HSCI or HyperSockets converged interface, essentially when you had both OSAs and HyperSockets interfaces, you had to configure different IP addresses for them and then set up routing in order to basically determine, do I need to route externally? I use the OSA. If I can route internally, I'll use HyperSockets. With the converged interface, essentially now there's a single IP address that represents both devices. And dynamically, we determine based on what endpoint we're trying to reach, whether we use the OSA or the HyperSockets interface. So in this example here, if LPAR1 wanted to talk to LPAR2, we would use a HyperSockets interface. If LPAR1 needed to talk externally, then it would actually use the OSA interface and go out to the switch and out to the network to get to it. So essentially that provides, so there is, basically combines both of them, but you can still provide isolation even though you're combining both of them. So in this example here, we are, segmenting the HyperSockets link. So LPAR 1 and 2 gets its own network segment for HyperSockets. LPAR 3 and 4 gets its own segment. In addition, the OSAs are also segmented because they belong to different physical LANs. In this case here, the zOS LPARs on the left belong to LAN A, and the LPARs on the right belong to LAN B. So there's complete physical separation between these LPARs using the converged interface as well, because we have different LANs for the OSAs as well as different chippeds so that we have different segments for the HyperSockets. Okay. So that's physical segmentation. As mentioned, that's, it can be, does take some planning. It does cost a little bit more because you have to have, additional hardware, additional switches, additional cabling, etc. Virtual segmentation is more a way to kind of still provide the isolation and the segmentation without the need for additional hardware. So the first thing we're going to talk about is virtual IP addresses or VIPAs. Hopefully all of you are familiar with VIPAs, but we have several different types and they play different roles in terms of segmentation. The first one is what we call a static VIPA. Consider this is a stack or a system-specific IP address. So in order to reach a TCP/IP stack on a specific LPAR or system, you can use that static VIPA. So what that means then is that if you have an application running on that specific or a workload running on that specific system, you can kind of segment based on that IP address. So if you give users only access to that static VIPA, they're not able to access anything else in the network. They're only able to access whatever that static VIPA supplied for them, the applications on that system. So it provides this ability then to do this kind of segmentation at a larger level on a system basis. It also provides, in addition to that, it provides kind of a high availability capability. So today, if you target a specific physical network interface, if that network interface goes down, you lose access to the applications on that system. Whereas if you target a static VIPA, well, if you have multiple network interfaces hosting that system, then you could reach that application over any of those interfaces. So it provides a kind of an availability standpoint as well as a segmentation advantage. The next type is a dynamic VIPA. So think of the first type is of dynamic VIPA is consider it just exactly looks and feels like a static VIPA, but it's configured using a VIPA define statement. What's unique about this is with the static VIPA, when you lose your system, you lose your static VIPA. With dynamic VIPAs, essentially what happens in a sysplex environment is you can basically say this stack is a primary owner of this dynamic VIPA, but now I am able to switch to fail over to another system if I were to lose this system. So dynamically, what happens is when that TCP/IP stack goes down that owns that dynamic VIPA, it will automatically get moved over to another system. So you provide that high availability in terms of being able to access that application. So the way that is done is those XCF links that we talked about before, we use those to basically send XCF messages across the sysplex so that we know exactly where that dynamic VIPA resides. So it kind of provides, again, that segmentation from a stack or system level. And if that system fails, we can basically move that segmentation practice to a different system that is serving as a backup. The second type is called an application-specific dynamic VIPA. This one is a little bit different. You don't define it with a VIPA define statement, you define it with a VIPA range statement. And that application-specific to VIPA only comes into existence when the application gets started and binds to that address. So what's nice with that one now with other dynamic VIPAs, which basically are associated with an entire TCP/IP stack on a system, application-specific dynamic VIPAs are associated with an application. So we start getting into now this kind of microsegmentation. So now you can have an application that owns an IP address. So wherever that application goes within the sysplex, it takes that dynamic VIPA with it. So now from an isolation standpoint, you can basically just limit users that need to access that application only to that IP address, not access to any other IP addresses in the sysplex. So essentially you're protecting yourself that only the users that need to talk to that one application don't have the ability to talk to any other application in that sysplex because they only will have access to that specific dynamic VIPA that is bound to that application. Okay. Now, the final virtual IP address, and this is the most common one, hopefully everybody uses this in their environment as well, is what we call a distributed dynamic VIPA. Think of this as a software load balancer that resides directly inside of the sysplex. Essentially, what happens is one of the TCP stacks owns that distributor IP address, and then there's a set of eligible targets where the applications are actually running. So when a request comes in to the distributor, he will forward to one of those targets. Again, this can be considered microsegmentation because, for example, suppose you have a set of CICS regions running in your sysplex and that it's servicing, it is providing a specific service. If you use a sysplex distributor to target those CICS regions, then everybody who uses that IP address will get routed to one of those CICS regions, but that would be all that they're permitted to. They don't have permission to use other IP addresses, for example. You provide this segmentation then on a workload basis by basically saying for this one workload that this, for example, Kix regions are providing for this service, you are limiting access only to those that application and not any other applications that are running in the sysplex. Another piece of segmentation is called virtual LANs. So previously, when we talked about the physical segmentation, where it's a matter of buying additional network interfaces so that you can physically separate the networks, well, an alternative is to continue to have the same network interfaces you have, but now logically segment them. And that is done through something called VLAN. Essentially, what that means is that each of these systems here on the left, for example, that are sharing an OSA, even though they share an OSA, if they all belong to different VLANs, the traffic as it flows is completely isolated from each other. So that means that the TCP stack A will never get any traffic except stuff that is for VLAN 2. Even though the OSA is shared across all three, only the OSA guarantees that anything that's tagged on VLAN 2 is going to get delivered to the zOS system on the left, zOS 1. So what it does then is now it's essentially taking that one physical network and logically separating it as if they were their own physical networks. So you do get the same benefits without all the additional hardware costs. You don't have additional switches. You can plug all these into the one switch. Now you'll also see there's something called trunk mode and access mode. Essentially what that means is that trunk mode basically says that in order, it will accept any VLAN over that port. And then, so in this scenario here on the left, any packets coming from zOS 1, 2, or 3 that's tagged will go through that one port. And even though it's tagged differently, the switch will allow all of them. And then it will determine based on how it's tagged, which of the outbound ports to go to, either VLAN 2, 3, or 4. So it provides that ability to do that segmentation. Access mode basically says the port will only allow packets that are tagged for that specific VLAN. So for example, in the middle one where we have stations 3 and 4, anything that comes into that port has to be tagged as VLAN 3 or the switch will not allow it. So that's a way to basically be able to do this logical segmentation. On the far right, it's the similar picture. It's just shared with dedicated OSA, but again, they can share the same network infrastructure in the same switch by individually tagging their packets dependent on what system they're going to. Okay. Virtual segmentation also applies to hypersockets as well. Essentially there, in this case here, previously, we had where we had the different hypersockets interfaces for LPAR 1 and 2 versus 3 and 4. Here we can have them share the same hypersockets interface, but we provide VLAN support over the hypersockets. So even though it's the same physical hypersocket link, under the coverage, we've logically split it into VLAN A and B so that communication can only happen between LPAR 1 and 2 over VLAN A, and that never can go over to LPAR 3 and 4 because they belong to a different VLAN. Similarly, for the converged hypersockets, these are very busy pictures, but essentially what it's showing here is that even though we have a single hypersockets interface that is shared between all the LPARs on the CPC, we've logically separated them by basically having different VLANs for the 2 LPARs on the left versus the 2 LPARs on the right. Finally, there's something called subplexing. This is not that well known, but previously when I talked about when the TCP/IP stack joins a sysplex, what it does is it dynamically creates network interfaces with all of the other TCP/IP stacks in the sysplex. It does this by default. So what that means is it's going to create hypersockets links with every system in the same CPC, as well as those XCF links with every system on different CPCs. In order to provide some type of segmentation or isolation in a sysplex environment, we introduce something called subplexing. And what subplexing does is we take that sysplex, and even though by default they can all communicate with each other, we can limit who they communicate with. So in this example here, the TCP/IP stacks on system 1 and 2 only can talk to each other. They are not aware of any of the other, by default, they're not aware of any of the other IP addresses or dynamic, sysplex distributor addresses, et cetera, that are in these other subplexes. So that means we can basically isolate or segment the network so that if I have a sysplex distributor running in system 1, we can guarantee that the only targets he could ever send to is either system 1 or system 2, because they belong in the same subplex. We will never, try to distribute packets to system 3, 4, and 5 because they belong in different subnets. Even within a given system, if you have multiple TCP/IP stacks, each of them can belong to their own subplex as well. So in this example here, you might be having, different use cases for those systems. You may have a development subplex where you want to make sure that only development work communicates between system 3 and 4. And you have an internet one that can communicate across all. So it's again a way to do this segmentation from a TCP/IP stack level using subplexing. And with that, I'll pass it off to Navya.
All right, thanks, Mike. So let's move on to the logical segmentation. There's a wide variety here. The first two are related to firewalling. The first one is network-based firewalls. These can be this is present in everybody's networks. They can be individual devices, or they can be multifunctional devices like routers with built-in firewalls, or IDS-based network devices with firewalling capability. Typically, a firewall in the network looks at the IP packet attributes like source and destination IP addresses, source and destination ports, or the protocol like TCP, UDP, or ICMP, as well as whether the packet is inbound or outbound. Some firewalls can dive into the application payload, so they can make decisions like SQL injection, or they can check for signature verification and things like that. So some of the advanced capabilities. Firewalls are typically maintained by your enterprise networking team. So it's typically outside the scope of zOS. They open up certain ports that need access from outside. So it's mainly focused on macro segmentation because it's permitting based on IP address or port. On zOS, we sort of have an additional capability called IP packet filtering. So you can define IP packet rules at that also look at IP packet attributes like IP addresses, protocol, port. But it can also look at whether the traffic is local to zOS or routed. It can also look at the network interface, the security label on the network interface, etc. The actions that you can take are deny or permit. There's also a third action, which is permit with IPsec protection. So our zOS IPsec protection is built on top of IP filtering capability. We're not going to get into that today. So there's two ways to configure these IP packet rules. You can configure a set of default rules in your TCP/IP profile, and this is to allow traffic that you want to allow before policy agent comes up. So things like OMP route, or if your policy agent traffic is coming from a remote system. But your comprehensive filter rules are defined in the policy agent for all of your zOS network traffic. And policy agent then installs those rules into the TCP/IP stack. We also have something called defensive filters that can be generated dynamically via an IPsec -F command. And these are basically deny rules. So say you're in an attack and you need to put something in place immediately, then you can easily use this command to put a filter in place. And this gives you time to determine whether you're really under attack and you need a permanent filter on your policy agent, or it was some misconfigured or misbehaving application that needs to be fixed. So you can do both macro segmentation as well as micro segmentation with IP packet filtering, because you can control which remote systems can access your local resources here. And I think we know at least one product out in the network that builds micro segmentation using the IP filter rules on zOS. So great capability here. A few considerations for when you use IP packet filters for microsegmentation. You want to make sure you use endpoint fire rules in conjunction as well. You can get very granular with IP packet filter rules, but you want to be careful with the number of rules that are generated. So there's no specific limit, but based on our observation, keeping that number to in the mid thousands works best in terms of performance. We've also seen that when the rules grow too large, pageant might even fail to come up due to insufficient memory. So that really depends on the memory available to pageant, but you want to keep the total number of rules in the mid thousands. One other thing to note is that IP security policy also contains your IPsec rules. So if you use something else to generate the IP filter rules, then you need to merge it with the IPsec policies generated by Network Configuration Assistant. So here's a picture of the Network Configuration Assistant, just showing the different technologies that are available. For IP filter rules, you want the IPsec technology as well as the TCP/IP profile technology. All right, so moving on to the routing tables. The most basic one is static routes. It's based on destination IP addresses. As the name suggests, it's fixed and unchangeable in most cases. And that means that even if the route is not active, it is still there. So you could lose packets if that route is taken. So not very resilient. Replaceable routes can be updated if they also have dynamic routing enabled, which we'll talk about next. So dynamic routing is also based on destination IP addresses, but they're managed by the routing daemon called OMP route on zOS. So OMP route monitors this routing environment, and like it has the capability to reach out to other routers in the network. And so it will know if a route goes down. And if the route goes down, then it updates the routing table automatically. So much more robust than the static routes. And this is a key feature that's used for the dynamic and distributed vipers that Mike talked about earlier as well. As those addresses can move around, we actually rely on the routing environment to advertise those addresses over whichever route is active. So static and dynamic routes are good for macro segmentation. Policy-based routing, on the other hand, can be used both for macro as well as micro segmentation, because it can be based on other factors other than just IP addresses. You can use job name, you can use the source and destination port, the protocol, what security zone is being used, and that security zone gets defined in the TCP/IP stack. So there are multiple factors that come into play there. And policy-based routing is also configured using policy agents. So you can use Network Configuration Assistant to configure those policies. So let's talk a little bit about policy-based routing and microsegmentation. As I mentioned, since we have several criteria, policy-based routing actually is useful in certain scenarios when it comes to microsegmentation. Say you want to limit specific workload to specific segments of the networks. For example, if you have a client and server that is supposed to communicate only over a specific route, then you can enforce that using policy-based enforcement. If you want to make sure that the traffic is tagged to a certain security zone so that the type of traffic can only be routed to an OSA that has the same security label on it, then that's where policy-based routing is useful. As well as if you want to separate out like the administrative traffic from business traffic, like card processing and things like that. One thing to note is that the policy-based routing only applies to local traffic, so it doesn't apply to routed traffic, as well as it's not compatible in the common INET environment where you can have multiple TCP/IP stacks, and we'll talk about that in a bit. The next topic is we have two fairly new technologies that have come out on zOS, which is zOS Container Extensions and zOS Container Platform. So let's look at how microsegmentation fits in there. So the first one is zOS Container Extensions, or ZCX. This is a case where you are running a Linux guest in a zOS address space, and you have containerized Linux applications running within that Linux guest. So when the ZCX address space is started on zOS, a dedicated ZCX deviper is assigned to that. And all the containers running within ZCX can be addressed through that ZCX deviper. So you can think of it as the Linux host IP address. In order to reach those containers running in the Linux guest over that deviper, the zOS TCP/IP stacks acts as a router here. So it's not an endpoint or the destination, it acts as a router to the Linux guest. So in terms of microsegmentation, the things that we talked about deviper applies here, as well as the points that we talked about routing and the IP packet filter rules for routed traffic applies here. So we also have something called zOS Container Platform, which is pretty new. Here, native zOS Unix applications can run as containers on zOS. So in this case, each pod, which is a Kubernetes term, gets a dedicated deviper. All the containerized applications within that pod use that deviper address, and they can communicate to each other using dedicated ports. So each pod here gets its own IP address and the entire port range. So note that the deviper and the port are local to the zOS TCP/IP stack here. So TCP/IP stack is acting as a local endpoint for these containers and pods. So in terms of microsegmentation, IP filter rules for local traffic and devipers apply here. There's a whole lot more to this picture. We're only talking about it from network segmentation point of view. And if you're interested in more than that, then Mike can talk to it. Couple more logical controls. So the next one is net access and port access rules. These are enforced using SAF controls. They're software defined. So the first one we have is net access SAF rules. You can define network zones, and then you can have net access SAF resource to determine which user IDs have access to that zone of the network. So in this diagram here, I have pub serve and prive serve, and I have network zones B and C defined. Sorry. Okay, so net access rules can determine which user IDs can bind or connect to an address, the ability to send and receive packets to and from a network zone. And the network resources can be the entire network, a subnet, or an individual host. The network security zones are defined on the net access statement in the TCP/IP profile. So here I have zone B, zone C, and default, which means the entire world, defined in my net access statement. Net access provides a one-to-one mapping between a network resource and a SAF resource name. So the SAF resource name would be something like ezb.netaccess.systemname.stackname.zonename. So on the left here, you can see I have zone B and zone C SAF profiles defined, and I have only pub serve permitted to zone C. So prive serve doesn't have access to zone C in this case. So a great way to control which user ID has access to which network. And just want to point out here that the fact that we're using the user ID to limit who has access to a particular part of the network is unique to this, and it's not something a firewall can do. Port access rules determine which user ID can access or can establish itself as a user on a given port. So basically the user ID that is associated with an application at the time of the bind request needs to have access to the SAF resource. So you would have a SAF resource, something like ezb.portaccess.systemname.stackname.safname. And that SAF name is what you would define on the port or port range statement in your TCP/IP profile. So in this case, I have a web port for port 80 as the SAF name, and I have a SAF resource called ezb.portaccess.star.tcp/ip.webport. And only pub serve here has access to that web port. So prive serve can't establish itself on that port. The last topic here is related to multiple TCP/IP stacks, and this is again pretty unique to zOS. We can have up to 8 TCP/IP stacks running on zOS. And this was introduced at the beginning for scalability purposes. That's really not, doesn't apply anymore, and we don't recommend using this. But so it's just more for awareness here. We have a SAF resource called ECB.stack access that controls which user ID has access to which TCP/IP stack. So in this case, PubServ has access to, only PubServ has access to TCP/IP-A, whereas PubServ and PriveServ have access to TCP/IP-B. To wrap up here, there's a lot of capabilities on zOS, and we just touched upon each one in brief. So there's a lot more information in the documentation. And which technologies you would need, again, depends on what your enterprise networking infrastructure looks like and what they're using to segment as well. But hopefully this gives you an idea of what tools are available on zOS, both in terms of macro as well as micro segmentation. That's all we had. Please do your session evaluation. It really helps us determine what we can present next time. Thank you very much for attending the session.
Thank you. There's one question in the chat. Do people still use multiple IT stacks? I remember we did, but merged them over 20 years ago.
No, like I said, it's not recommended to use anymore.
Right. But it's interesting. It depends on the geographies. Some geographies tend to still use them more than others. But you, as Navia mentioned, yeah, the intent here is because there's a level of complexity involved with Common INET that there's no real reason in terms from a scalability standpoint, which is what the real reason was initially for it.
Thank you. There are no other questions. No, there doesn't seem to be any other questions. Thanks, Mike and Navia. Thank you very much for supporting GSE 2025, and we'll end the meeting now. Thank you.
Thank you.